YouTube till it gets on. It's like there's an old movie, Wayne's World. Remember that? Anybody watch it? The 5, 4, 3. It looks like we're on. Okay. Good afternoon. I want to start by first of all, thank you for coming back. It's nice to see you. I'm pointing at the web page to begin with because I had sent an email over the weekend about homework assignments. First of all, if you didn't get the email, let me know because I don't have you on the list and I need to add you. But if you did, I hope you've taken a look. I just wanted to go through a couple things first to get things familiarized with you. I don't think the homework is too demanding yet. I hope it's not. It's more, there's no math involved yet. It's more just kind of get through things. So on the website, if you scroll down below our course list, our topic list into the homework schedule, you'll see there's a homework 0 that's extra credit and there's a link to it. If you click the link, it pops up something called the Hoffland Homework Hub. So my wife is Lisa Hoffland. I'm Jonathan Templin. We have a son, Hugh, whose last name is Hoffland, combination of our last names. So that's where we get that from. It asks you to sign in with your last name, so I can do that here. Oh, there we go. And your 7-digit KU ID number. Now that should be the number that's on your KU card. It's the one that I find in enroll-in tags. And when you do that, it takes you into the homework system. Now on the homework system is where you'll be able to find your grades for the class. When things are graded, it's there. But also homework 0, 2, 4, and 6. All the even homeworks and the number 0 will be online. Homeworks 1, 3, 5, and 7 will be offline. But once the grades are done, you'll be able to check everything for grades up here on class. But homework 0 is right here. If we click begin or continue, you can see the questions. These should be fairly self-explanatory. How many of you have done this already? Almost a number of you. So it was successful? Okay. We think.
Yeah,
well, here's the thing.
September 1st. Yeah.
You'll find out, but there's some parts of this that you can find out immediately, and that's the part that I wanted to go with. I just said there's 7 homeworks, so you know the answer. But if I put the number 5 in and I hit enter, it turns red, right? I'm not trying to, by the way, you should get all 3 points on this. If you didn't, then we can fix it and you'll get 3 points. It's okay. And these are extra credit points. It's really just to try to familiarize ourselves with the system. I do this because there's a lot of things that involve, when we get into the R part of this class and the computation, there's a lot of things that involve syntax, and we don't really have a lab component, and it's really hard to kind of check your work when you're going along. So this section right here is built to make it so you can check what you're doing syntax-wise. When we get into CFA, the first CFA homework, which will be homework number 2, we'll ask you a bunch of different questions. You'll have to build a model, you'll have to run the model, and have to interpret the output, right? So the first part will be a bunch of questions to see that you ran the model correctly. And while I like this idea, and Lisa wrote this homework system when we were at Nebraska together, and we sort of had input on how things work. We thought this is a great way of checking, right? You don't have to, you can double check, but it's also really maddeningly frustrating, right? Because there are times where you might put a number in, think that you're right, and have it be like, what? Red. And so you try again, and you try again. And I will say, when you get into that spot where you've tried multiple times and you're just not getting progress, you're welcome to email me or Lou for how, hey, I'm trying this. When you do that, send us your syntax. And probably the data too, so it's easy just to download and troubleshoot. Yeah, Jesse? For
times where we do have, and I imagine you will, some kind of rounding, will you tell us the number of decimals?
Yeah,
we'll be expecting?
0.001 is what it says up here.
Okay.
I actually think it's less stringent in the system itself. I think it's 0.01. It depends on the homework, I have to set it myself. But I do that because actually what I've done this semester, all this homework, it's first of all, it's great, but it's also really clunky on the code side. So and it's not no small feat. Lisa wrote it all in SAS, and so I'm borrowing it. I wrote another system in R using her SAS code, translated all to R to make it work, and I do that with my multivariate class when I teach 905. EPSY 905. But this is all back in SAS because it's hardwired with M+ script that she uses from her class. And we're going to see, I'm having Lou, or TA, test to see that R gives us the same numbers as M+. So it's mostly consistent. There may be a couple questions I have to change here and there. Long story short, it's built that way because they do start to diverge after 3 decimal places sometimes. So it's not that big of a deal. M+ has bigger issues. One of the first things we found was that if you use M+ on a Windows machine and you run it on a Mac, for instance, or you have a 32-bit processor and you have a 64-bit processor, it'll give you different results for the same model also. And that's a coding thing that they didn't lock in the specification for what floating point number should be, and so because of that. So this is why we use R, first of all. R has it fixed, and it should give you consistent results across platforms and compilers and, processors. But it should make it work here. So long story short, yes, probably 3 decimal places, but it'll round it and make it. There's some wiggle room there. My goal, okay, so now, you want to grade in the class, and look, you're going to get an A most likely, right? You just try, but my goal with this, you can, shortcut it by, if you think you're in the ballpark with a number, you can start trying other decimals or whatever. My goal is to try to make it so that it's a guess and check type of system, to just make sure that you're on the right path. So try doing that. That's my goal. If you get to the spot where you're, struggling or whatever, realize that if you don't get the homework done on time, it's not a whole lot of a penalty. It's 3 points. It's not a lot. Plus, there's extra credit opportunities as we go through the semester. So I would like you to try to learn it more than circumvent it. Anyway, I know how school goes. It sucks. Semesters are tough, and then when you get into October, that's when I hear the things just go off. The wheels come off the cart. Something like that. Questions on this? Everybody found those of you who did this were able to log in and it worked just fine? Awesome. At the end of it, by the way, if they haven't done this before, you have a spot where you have to save your answers. Then if you want to submit the final answers, you push a button and you type your ID number again and then submit. So, there we go. Cool. The other part I wanted to talk about was homework 1, because this involves a little bit of planning on your part. Homework 1, by the way, homework 0 due this Friday at close to a minute before midnight. And then homework 1 is due a week from Friday at 11:59. And it is a task where I gave you a Word document here. Let's see where this pops up. It's thinking about it. There it is. And the goal here is to get you to take a survey or a scale or an instrument, something you're familiar with, preferably that you might have data on, and to take a look at it where it began, what its history was research-wise. So it asks questions like, what population is this? What's the latent trait? What are the format of the items? How many dimensions? How do they evaluate? Do they provide evidence to support how many dimensions that were in the instrument? Did they use PCA or EFA, which is the topic of our course today, or CFA? They talk about reliability, validity, and so forth. And what do you think? Do you see any potential problems here? And so, invariably, this is the first time I've given this assignment out. I've talked to Lisa for years about this, and she's done this assignment for years. And what happens is that if you're in a lab or you're in some type of research group, you'll use an instrument that your group has created, right? And that's where eye-opening things happen. Now let's imagine that you're not using your own, you're using someone else's. Like, let's say the BASC. Anyone use the BASC? All right, there you go.
Behavioral assessment skill for children.
That's right. That's right. When I worked at the University of Georgia, Randy Camphouse was chair there, and he's the guy who created the BASC. He was chair when I was hired, so know him a little bit. Turns out the evidence for the BASC not the strongest. If you go back to the original, so this is what you'll see. Whatever scale you have, if it was developed 20, 30 years ago, probably using EFA, maybe classical test theory. And when you start to apply the modern versions of measurement models like CFA to it, nothing fits. It's a very eye-opening experience. Doesn't happen all the time, but it happens quite a bit. So be prepared for that. It's more just a thought of what's happening and how it works, and why is that the case. That's what we're hoping to get into. Okay. Is anybody looking at the live stream right now by any chance? I keep seeing it flashing, and I don't know if that's a good thing or a bad thing.
It says that you are live.
It says I'm live. Well, that's good to hear. At least I'm live. And it looks like it's fine over here, but I don't know. Okay, well, I'll just assume it's going well. If not, I'm sorry, everybody.
Yeah, I think it's working.
Oh, good. All right. Any questions on homeworks? Okay. Cool. You guys are pretty laid back. I like that. I'll try to be laid back as well. So today we're talking about my favorite topic. Not at all. My least favorite topic, exploratory factor analysis and principal component analysis. This is lecture 2 on our plan for the syllabus. This was supposed to happen last week, but we're going to make it all fit into today. Next class, we'll talk about classical test theory and be done with that too, and then we'll just forget the first couple weeks of the semester.
So where should we be in the readings?
The readings, good question. Let me pull them up. I'm sort of the mindset. I'm taking a different track this year where I feel like, excuse me, this is the syllabus here. I'm sort of less, I'm not as strongly emphasizing the readings this year, and that's because I'm not a big fan of most of them. So, if you're not reading a whole lot right now, I'm not really upset. So I would say if you're interested more in kind of the big picture, that first article would be the first where to go. If you're interested in a little bit of EFA and PCA, there's an article by Chris Breacher and Bud McCallum. If you really want to get into more stuff, I'd say, I'm not so wild about that. The McDonald chapters are good. I like those. It's more of a classical test there. I'd start, really focus on those. And if you want to read ahead a little bit, Brown's chapters. Those are very readable and accessible. I love McDonald's book. That was the first one I got into. But I'm only giving you snippets of it. So does that help?
Yeah.
Yeah. So, okay. Yeah, I have this goal. I think I'm going to write a book on this for the subject, perhaps with Lisa in the next few years, and so we'll have our own chapters that go with it. But I'd like to blend in Bayesian statistics with it too, so make it more of a real contemporary type of class, but not there yet. So, yeah. Thank you, Hatice. Is your name Hatice? I'm getting it, working on it. Okay, so what are we doing here? Exploratory. You've all had exploratory factor analysis before, I take it. You've had PCA. You probably use it. Those of you who worked with John Poggio, you probably have EFA pajamas. Actually, some of my colleagues have PCA pajamas. Yeah, seriously, PJs that are rotations and stuff. No. So what we're going to do, our course is dedicated to latent trait measurement models as part of it, and then what we do with them in regression, which is the structural equation part. So, confirmatory factor analysis and item response models and so forth. But really, we're going to start with EFA and PCA to try to talk about how these are similar to the confirmatory methods that you find, but we're only going to talk about the high points. The key thing with this and why there's two features of EFA, and PCA really, why I'm not really keen on using them. The first is that the results themselves are not very stable, right? Meaning if you take your data set and you run an EFA or a PCA, and let's imagine you try to figure out the number of dimensions you have. Somehow you look at eigenvalue, something called the eigenvalue, right? And let's imagine have you heard of bootstrapping before? Where you basically resample from your data set to create the same data set, the same size you resample with replacement, right? So you do that, and you just bootstrap your data set get a brand new resample, use the EFA and PCA, how likely is it, do you think, that you'll find the same number of factors? Not very. No. Right? The same thing goes with cross-validation, where if you take half of your sample and use a PCA on it, then go and try to see if the same thing holds in the other half, it's not likely to fit. So these things are really unstable. But beyond that, I want to make a mathematical argument that EFA really is equivalent to CFA in the structure. Now, PCA is a little bit different. It's its own matrix algebra technique. But there is a mathematical argument that's being made that to make either of these models work, we have to make certain assumptions, certain constraints, we call them. Right? And in the CFA world, we can easily figure out what those are. What is it? There's a constraint. We have to set the scale of the latent variable. We have to somehow figure out its mean. We have to somehow figure out its standard deviation. Right? Because it doesn't exist. So things that don't exist, we pick its scale. Now, there are 4 or 5 methods of doing that. We'll get to that in a couple of weeks. But that's basically it. There's these certain constraints we have to impose to make things work. Well, the EFA has those same constraints, and sure enough, the things it imposes on it are really crazy. Like the sum of all the factor loadings, the product of the factor loadings, times the unique variance for each item. Sum that all together, that thing has to be equal to 0. What? What the hell's that? I don't know. So that's why I don't like it mathematically. But more often than not, the EFA and PCA give you misleading results for a factor analysis, trying to figure out the factors underneath your items for multiple reasons. If your data don't meet the assumptions of EFA in particular, which is normality, if you have non-continuous data, which pretty much everybody has, you might get misleading results. Your constraints are implausible, which is EFA. That's a problem. Also, the sample itself, it's very highly sample dependent. Right? If you've got hundreds of thousands of people, it's probably going to be pretty stable. How many of you have those samples? Someone usually in class, I do. Good. They're those people that live behind the gate, you know, on the big swimming pool. Anyway, so, but but bigger picture to all that. So there's the mathematical argument for why not to use it, which to me, it's equivalent to CFA, but with crazy, crazy assumptions, for EFA at least. But then there's the other philosophical argument, which is, like, why on earth don't you know anything about your data? Right? In what situation did you ever find yourself where you've got a survey, and you've got a bunch of items, and you say, you know, I have no idea what these things measure. Right? Have you ever been this? Like, why do you build an item in the first place? I'm trying to think of a situation where this would be. Like, maybe there used to be this TV show, I don't even know if it's on anymore, Storage Wars. You ever heard of that before? Or people would bid on, so like, the storage lockers that you can rent and put your stuff in. Like, if people didn't pay, they defaulted on it, then there's an auction that happens for them. And they don't open the door yet. People are bidding on what's on the inside. And so, like, if you're that bidder and you win and you go inside and there's a bunch of data and there's cryptically written questions, maybe, right? Alternatively, you're an archaeologist. You're digging around and you found, I just saw this article about, there's a base 60 number system that the Mesopotamians had somewhere in like 2000 BC.
Trigonometry easy.
Yeah, something like that, right? And so like people would say trigonometry was often attributed to ancient Greece, but really it predates ancient Greece by at least 2,000 years, which is pretty cool, right? Now, if you found a survey, from ancient times, Mesopotamia, written in whatever language was the time, and printed on stone, where the data were on tablet form, yeah, I get it, right? Why do you write items in the first place, though? For you, you know why you're writing the item. It measures something. You know what you want to measure, right? It's not your data's job to tell you what it measures. You should have a clue as to what would happen. Now, there are some of people out there who would say, yeah, but okay, I know all of that, but EFA is this magical black box that's like a fortune teller, right? It will tell me the fortunes of my data. It will tell me the number of dimensions I have, and it should discover what's in there. But unfortunately, like most fortune tellers who are out there, they're just a ripoff. EFA is not really going to tell you that, right? You go to a fair or a carnival, the people are like, I'm going to guess your age within 10 years, or you take a look at, I remember years ago, there was a guy named John Edward who was up there who would always he's this master psychic who would understand things, right? EFA is no psychic, really. It's giving you misleading information. So this is it. So big picture, philosophically, you should know what's going on in your instrument and seek to confirm that. EFA, probably not going to do that. So EFA versus PCA, though, come from two different schools of thought. On this. So EFA, exploratory factor analysis. PCA, principal components analysis. The theory, the actual model that underlies EFA, came about at the same time that people were really doing good things with principal components. Problem was, we didn't really understand, we didn't really have computers at the time. This is like the 1930s, 1920s, 1930s. Didn't have computers. We had an idea for how to estimate the EFA model, but the computations behind it would take forever. So it turned out we used PCA as a crude approximation to do EFA with. That's how it started. We still continue this because there are textbooks and there's God knows how many classes that we teach on the topic of this is the way. But that's the way if you didn't have a computer, right? Or didn't have access to a computer, right? I mean, even in the 1960s, nobody really had a computer in their house. But a lot of people had access to a computer on research campuses or other places. So the two schools of thought about EFA and PCA are, the first is that they're entirely different things. How dare you put them in the same sentence? And the second is principal components is sort of a device, a crude way of viewing EFA. But really, principal components, there are different versions of principal components that get used to do EFA for. Right? There's ways where we'll turn around and take a covariance matrix and trick what's on the diagonal, or take a correlation matrix and trick out what's on the diagonal for it, and then do PCA on it. Right? That's sort of that EFA people saying, well, this is almost what we need it to be, so we're going to make this work. The true PCA itself is just it's a description of a data, right? It's a way of taking a matrix. Take a square symmetric matrix. And actually, if it's not square and not symmetric, there's another version of it called the singular value decomposition. But it's talking about what's the rank of the matrix, essentially. What is the size of it? We use this in matrix algebra all the time. We use it in data reduction all the time. Like, where I found it to be very useful is, you've seen some of these large surveys, opinion surveys like this too, where they survey the nation, but they sort of oversample certain groups, and so they want to reweight by which, to make it more even with the population at large. If they collect 300 demographic variables and want to sort of reweight based on the 300, a common method of doing so is to create composites of those 300 variables using principal components. They're not doing so to go and interpret the features of these 300 variables as 4 factors, but no, it's a way of making a 300 variable problem much smaller. So I've seen that done before. I don't have a problem with that. But with respect to saying there's factors and these are things that represent people, it's really hard to go with. So, the primary purposes of these. Number 1, how many factors do you have? EFA, a number of latent variables. And then once you figure that out, what do those variables mean? So EFA, what are the factors? And then which items relate to those factors themselves? What do those factors mean? How many, I think the 2 questions are, how many factors do I have and what do those factors mean? In PCA, it's a little bit different because it's this pure kind of mathematical mechanism. it's ultimately truly a data reduction idea, right? It's not ascribing meaning to the like pure PCA is not ascribing meaning to the components, right? You still have a number of components. They're now a kind of a mixture or a combination of the variables weighted by the eigenvector elements themselves. But PCA as a trick really is to try to say, okay, I've got. If you think about it this way, remember the history of the internet. How many of you had dial-up internet when you were? Okay, most of you, right? Remember, you know how long it took to load an image?
Wow.
Right? Yeah, right. So remember this dial-up sound. Remember how slow it was? And like the images, well, the image that came up on the internet was a JPEG, right? Which was a compressed version of a bitmap, right? So a bitmap is every pixel has 3 color values, right? Roughly speaking. And the JPEG used a PCA type approach to effectively give you the same picture but with a smaller size, right? It wasn't going and saying, hey, dimension 1 is red and dimension 2 is green. It was basically saying, I want to give you roughly the same idea, but fit it through your modem. If you remember the modem back in the day, right? So PCA is very good for that. For EFA, though, what we're really after, we're not trying to reduce our data. We're trying to describe a factor. We're trying to describe this construct that's supposed to represent the mathematical mapping of behavior onto some scale, right? So typically, if you go look at a book like Tabachnik and Fidel, which is one of my least favorite multivariate books. Now listen, so Tabachnik and Fidel were, I believe, professors at Cal State Northridge, if I'm not mistaken. I'm a graduate of Cal State Sacramento, right? So there's this university, there are several tiers of university systems out in California, right? There's the UC system where Berkeley is, and that's like PhD granting institutions. Then there's the Cal State system where very few, actually none gives their own PhD by themselves, but some, have dual programs with UC schools to get PhDs. What that means is essentially they are programs that are commuter schools. They really help me. They have large student bodies, but they're interested in 4-year degrees and maybe masters. So Tabachnik and Fidel were in a psych department at Cal State Northridge, and they were teaching a master's class. And so basically they needed something to show up after someone has taken the linear model sequence. Or better yet, they put a book together to try to do that. So what shows up when you have 2 years and you have this small compressed program? Well, let's throw everything we might need to throw into a book. We'll call it multivariate. So you see logistic regression there, right? You see exploratory factor analysis. You see all of that. So the purpose of that book really served what they were doing well. But where my problem with it is when you're in a situation where you've got a little bit more specialization or you've got a PhD level type of degree, you can't quite just take the broad thing and have it fit everyone. So, me not trying to rip on Tabachnik and Fidel and what they were trying to do, I just don't like their book for that reason. But here's an example of a survey. You're supposed to hypothesize the number of factors you're supposed to measure. I don't know why 5 or 6 is recommended for a stable solution. That doesn't make any sense to me. 1 is really stable. What you want to do then is take, for each of these factors, get 5 or 6 good indicators. Now, the word indicator really means item. I prefer thinking of an item as an instrument of measurement. So I say an item measures a factor. It's a measure of a factor rather than indicator, but that's another indicator for a comment. So some should be markers, which is really sort of what kind of the key idea is. You really want to avoid multidimensional indicators. Now, I work in a research field where we study multidimensional things, so that's sort of old for me, and so forth, right? And then you get a big enough sample, and then that seems to work, right? You put it in the machine, and then you figure out whether you're going to use a EFA or PCA. Right? So anyway, don't quote this. This is all antiquated, right? Why this? Here's how I look at it, right? If you're trying to measure something, you measure it well, right? what the items are matter. So how related that item is to the construct really makes a difference. And where that starts is with the kind of the face validity, right? The idea this, you know, if I'm measuring happiness, the question, are you happy right now, should be on there, right? Because that's central to the construct. But not only that, the more items I put on if I really want to measure the construct well, if I'm interested in precision of measurement, 5 to 6 may not be enough. Probably isn't. Most likely you need something like 18 to 20 to get a really good reliability, right? So when I look at this, I think, oh. Then I look at thinking a multidimensional ideas. Well, if you have a construct, certain constructs map onto multidimensional factors and multidimensional items quite well. If you think about math tests, particularly math. I mentioned this grant I was working on at Georgia with math educators about us building this very nuanced part of proportional reasoning. Pretty much all of our items measured more than one. The next generation science centers, I've heard these before in education, but they talk about writing items that effectively you have a certain science area or a concept area, a core concept, which is like biology. But then you might have some type of method of using, like the item talks about a research method that might cut across areas, right? So maybe you're using something that came from physics, like some type of, or you know, if you're in archaeology, how do you know the date of the tablet that you just found underneath the ground? And that's, you know, some type of, you know, spectral measurement of exactly. So there's certain things that cut across science that you use, and so each item itself is inherently multidimensional because not only are you measuring something about the content area biology, but you're also measuring something about the method, right? And so they have to be that way. So I don't think that's necessarily true either. Multivariate normality was also a key. We always needed everything to be multivariate normal, and that's no longer true either. So all this is like, if you're writing notes down on this, just realize everything that you learned before has probably changed or read before. Okay, so first step, choose an estimator or extraction method. Now that's one of the things that's an indicator. That right there is evidence for me of why you shouldn't use this. It's the marketing campaign. Where else do you hear the word extract? Have an extraction.
Dentist.
The dentist, exactly. Actually, I had a dentist in Georgia, and she said, "All right, so what do you do?" I'm like, "Professor, I teach statistics generally." She's like, "Oh no, you and I are common. Like, we have a lot in common." It's like nobody wants to see you, and nobody wants to see me. Right? But yeah, if you're going to pick something that sounds like pain or, you know, don't use it. Anyway, extraction methods. We're just going to rip the teeth out of the data. School of thought number 1. How many factors do I need to reproduce the correlation matrix? That's usually what we start with. We have a correlation matrix of our items, and we throw it into this thing. So what we do, the primary difference between PCA and EFA, in PCA we take all of the variance, and in EFA we analyze what's common, kind of the R squared, the common variance among each of the indicators. This is the difference between the two. PCA, you just throw your correlation matrix in as is with a diagonal of 1s. The EFA versions of PCA instead throw the correlation matrix in with something down the diagonal. It's not 1, like they use a commonality or a uniqueness or something like this. But then what you end up getting is in PCA, the number of components is equal to the number of possible components, in this case, quote-unquote factors, is equal to the number of variables you put in. Right? So basically, you come up with it, and how it works is each component is a weighted sum of each of your items. If I is the item and L is what we would call a sort of an element of the eigenvector itself, this is just a mathematical convenience because we can actually quantify the sum, we can quantify the variance of each of these components, and sure enough, the total variance, the sum of the variances of the components, equals to the total variance in your data, right? But the first component will have the highest amount of variance. And not only that, it will be orthogonal to the second component, right? So it'll be completely uncorrelated with the second component. So that's it. You pick a level of variance you want to account for, and you call it good. You see how this works. Blah, blah, blah. We're glossing over, please. Questions? Does it all sort of jive with what you learned about PCA? Fit? No?
Well, PCA is spoken a little more positively.
Yeah.
They always use the word the Kaiser principle, which has something to do with eigenvalues greater than 1.
Mm-hmm. What? There was a quantitative psychologist, the last name of Kaiser. So I'm part of this group called SMEP, the Society for Multivariate Experimental Psychology, which my wife calls a society of old white guys. So I fit the bill. It's very restrictive. Someone actually died and I got it. And Kaiser was part of this group too, and to tell you the type of person Kaiser was, he put a bicycle horn on a box. It has a box that has a red light, green light, and yellow light for people talking, and when they get to the red light, if you've overrun your talk, you get the horn. It's called the Kaiser box. Anyway, Kaiser's criterion works the same way, right? Effectively, it's this. If you have a correlation matrix, and you're using an EFA on it, the total variance. Now remember in multivariate, did they teach you what the total variance of the matrix is? It's the trace. Do you remember what the trace of a matrix is? It's the sum of the diagonal elements. Right? So the total variance that you have in a data set is the sum of all the variances. Well, a correlation matrix is a covariance matrix of standardized data. Right? Meaning when you standardize your data, every variable has a variance of 1, a standard deviation of 1. So the correlation matrix, total variance, is equal to the number of items you have. And each item contributes 1 unit to that total variance. And so the Kaiser idea is that if you have a component that accounts for more variance than one item normally would, it's worth keeping because it's describing a little bit more of the total variance than what one item would by itself. Yeah.
So I figured it had that we had to have had standardized matrices before we started looking at it, because otherwise the values of the eigenvalues are arbitrary.
Exactly.
So thanks.
Yeah, that's exactly it. So, and that's where this correlation matrix comes into picture with.
But I'm not sure if this is right, but this is what I thought about it, because it assumed that there is no correlation between the items, which is not true. It's not accounting.
Yeah, it says there's no correlation between the components itself. There is a correlation. You have to have a correlation with the items. If you put a correlation matrix that's just the identity, so zeros in the off diagonal, no correlation between any item into a PCA, it will return to you every component will have variance 1. It'll be each item by itself. So you have to have the correlation with the items, but I think what you're talking about is these C's, once we make the component, are uncorrelated. Yes, we do that because that's how we can, one of the nice things about PCA, when you do use it for data reduction, is that it or makes sure things are orthogonal. Basically, with the lack of the correlation, it means each bit of variance it's describing is unique to itself. Right? And that's part of the method that does it. We can't handle that, so this is part of that, that mapping of the idea of factor analysis onto PCA. Well, we can't possibly use that. We can't have our factors be uncorrelated. They come from the same head, for heaven's sakes. What do we need to do? Rotate. Right? We need to find a way. But no, the pure, what am I talking about? The most basic elemental output from a PCA is a set of components that are uncorrelated, completely uncorrelated. And it's a benefit in many uses of PCA, but not in the mapping of factor analysis. How are we doing? Okay. So, yes, but basically this, what we want to do, we say the number of indicators we pick, we see the eigenvalues of each, which really describes the total, the amount of variance each one accounts for, or the set of the component, how much variance it has. And then we go and figure out what it means by the weight of each of the, in this case, I'll put in quotes, loadings. So they're really the elements of eigenvectors, their properties. Here's the other fun fact about principal components. The actual loadings themselves are not unique. Right? Does anyone remember, you took multivariate, did you talk about eigenvalues and eigenvectors a little bit? Well, you didn't. So you get each matrix, each one of these square symmetric matrix has a set of eigenvalues, and each eigenvalue has a vector, and that vector represents each of these weights. But to get the weights that you see in the computer, we have to say that the length of that vector is equal to 1. Right? So for every, it sort of became standardized that we say we're just going to make the length of every eigenvector 1, and then you get a set of weights. But it turns out that's just an arbitrary choice. You could say the length is 10. Well, then the weights change. I mean, they change proportionally. They are all about the same. So that's another weird feature of it. You have to start making some assumptions about what you're doing to make it work also. Anyway, it's a mess. So eigenvalues, eigenvectors. I'm not going to go much into this. You don't. Let's just make this agreement. If someone wants you to do a PCA, do it because you're at grad school. But when you graduate, please don't do it. Yeah, Craig.
So if someone was making you do a PCA, would you go with the Kaiser criterion, or would you go with like the screen tests from Gorsuch?
I'm out of grad school, so I'm done. I don't work with them.
What would be...
If I were in your state, no, because ultimately, if they're irrational enough to not believe math, then ultimately you ask them, what do I go with? Because that's going to change too. Whatever you pick, they're not going to take that. That's pretty much what I'm going to say. Okay. Yeah, I'm using PCA as my indicator of willingness to understand math and science. Right? It's unreliable. It's a one indicator, one item test. Right? It's not a very reliable measure of a factor, but that's my own thing. Anyway, I'm not giving you the full math here, but if you'd like it, come talk to me. I can show you the math we did and show how it works.
But still, it's a kind of you can use it like an indicator, but not the just one method to decide or discuss your data. You can use it just to give you an idea. Then maybe you can go, because I believe, based on my reading and my experience, that not for the PCA but for the exploratory factor analysis, if you decide and you have a good decisions about the appropriate models and the appropriate way of extracting the models, the number of factors, and if you rotate or not, you might get the same result.
I disagree. No, I don't agree at all. I think what you'll find is that it's luck if you find something that matches EFA and CFA. And that's for a number of reasons, but I don't agree. But not only that, let's put this into a context that we probably know a little bit. If you're doing analysis of variance, how do you know that your treatment effect works? Significance is one, effect size is another. Okay, if you're in an EFA, how do you know that number of factors you're extracting is significant or significantly different from another number? Have you done EFA where you had significance tests before?
We cannot do it. We do it with the
likelihood ratio test. Yeah, but you know what you're using then? You're using the CFA algorithm. If you're going to get in that ballpark, then we're now on the, okay, so yes, if you're going to use maximum likelihood based version, you're in a better spot because now you're equivalent to CFA. But the next question is, what constraints did you put in? But another thing with it, all right? So how did you figure out an item worked well? Let me see if I can get here real quick. Blah, blah, blah. How did you know an item worked well? Well, you take a look at the loadings, and which items loaded, what was the value of a loading you were taught that said an item was measuring that factor? The loading was bigger than 0.3.
Yeah.
Why 0.3? Is 0.3 significantly different from 0? So why is it this method you can get away with not having to be accountable for science or have evidence that's strong that says one thing or the other, whereas almost everything else that you try to publish, you do? That's what I want to ask.
Some gentleman from SMEP told us that
this is SMEP back in the 1960s. Actually, SMEP got started by the way, this is I'm sort of mocking this organization. When I was a grad student, Rod McDonald was in SMEP, and then I remember going out on the job market. Well, all the quant psych jobs I was trying for, the SMEP students were getting interviews and getting stuff. And it could have been I wasn't prepared or whatever else, but I felt very left out. Like I interviewed here at KU, and I interviewed against, I believe, 2 or 3 students of SMEP, advisors in SMEP, and then there was me. right? And somehow I got the job. So, you know, clearly it worked, things were fine, but I felt like, oh, well I like being in Smith because I give my students opportunity. Right? So it's like, oh yeah, now I see the table. But mocking it, it got started by Ray Cattell. Anyone heard of Cattell before? So he, what's that?
The same Cattell from the Cattell, Horn, Carroll intelligence theory?
Absolutely. John Horn was part of, was that? I don't know if Carroll was or not, but John Horn was a long time.
Carroll did his stuff separately and he merged the stuff later.
But yeah. What else do you know about Cattell? He had a Lifetime Achievement Award in 1990 from APA that was rescinded for his work in eugenics. I'm trying to paint a picture of the guy. He was rejected once at the Psychometric Society, one of his paper was. And so his response to that was he's going to create his own club where everybody could talk, but only he gets to, or they get to decide who comes in. So don't trust so what you get in there when you go there is this very well-published, very well-read people, and we're very smart. Don't get me wrong, but it's not a wide sampling. It lacks diversity in the scientific sense, not just a gender and ethnicity or research-focused sense. And so I think part of that is you get really homogenized opinions and that are amplified. And so yes, if somebody from SMET told you to do that, probably what you end up hearing. But ultimately, no. The PCA EFA evaluation of whether an item measures a factor or how many factors you are, using PCA, you don't get a significance test. Right? Now, you could bootstrap and try to come up with one, but who does that? How many people do you know who do that? Not many. So, but let's get here. So PCA, again, PCA is a legacy. It's Windows 98. Windows 3.1. Anyone use Windows 3.1? I'm getting old, so I'm having fun with my age. I'm like, yeah, I did. Like where you had to like type something at the DOS prompt to get Windows to open. And that's it, right? So this is what happened. So PCA came along. It came along first, and you could do it. And so EFA sort of glommed onto it as, hey, we're going to do that. But certainly after PCA, certainly after we got better computers in the 1950s and 60s and 70s, we sort of stopped doing anything with EFA. In fact, there was an article recently. So M+ will do EFA for you, and it uses by default a very weird rotation method, GeoMin or something. Exactly, it's some odd one, and it was cited there because someone wrote a book chapter in 1986, and this one method worked better for the Thurstone box data, which is the length and width and height of boxes. But in this article describing it, Michael Brown, one of my heroes in the field, also a member of Smith, had said, they had written about it, and he had speculated, this article was like in 2003, so that if you look at the history of literature in the statistical part of this, the EFA rotation method stopped getting published effectively right around 1968. What happened at the same time? CFA software came about, theory and software. We had the theory paper, there was a Yorskog paper in '69. Lizerl came out shortly thereafter. We stopped using it. So ultimately, if you're using PCA-based methods, you're using Windows 98. Windows XP. But then ML came along. Now ML, ironically, has been around just as long as EFA or PCA has. I mean, the 1930s were big in development of maximum likelihood. So if you're going to do EFA, maximum likelihood is the way to go. Because maximum likelihood gives you some protections that PCA doesn't. Number one, it fits a factor model. And it actually fits the model rather than using some type of matrix extraction. It actually fits the model the way you're trying to do. And you're trying to figure out the parameters of the model that maximize the likelihood of the data. So if you have to do EFA, start there. However, it uses the same functions that CFA does. Oh my goodness, right? So what does ML give you that I'm going way off the slides here, but that's okay. What does ML give you that PCA doesn't? It gives you, because now you, how many of you took Billy's multivariate last semester? A lot of you. And maximum likelihood, when you have a parameter maximum likelihood, do you remember the properties of it that are good? There are three good things. Right? So when you estimate something in data, as long as you have a big data set, you know three things. Number one, it's asymptotically normal, right? So as your data set gets bigger and bigger and bigger, each parameter you're estimating has a normal distribution. That's a good deal, right? Because now we can use that to give us a p-value for each one of our loadings. We can figure out where that loading falls on a normal distribution and tell you whether or not it's significantly different from 0. That's huge. Number 2, the estimates are what we call consistent, meaning the bigger the sample size gets, the probability that they converge to their true value is 1. As the sample size goes to infinity. That's huge also because that means effectively there's a right answer, right? You get a big enough sample, you get the right answer. And number 3, they're relatively efficient. There's no other estimator that's gives you a smaller standard error on your parameters than maximum likelihood. So ML gives you these great properties that you don't get when you're doing PCA, and you don't get if you're doing the EFA version with PCA. But part of that is you get the ability to do significance tests for each of your loadings. There's more evidence as to which one fits. It's not just 0.3. It depends on effectively an effect size. You can quantify an effect size also. But number 2, in maximum likelihood, it enables the use of likelihood ratio tests, right? Which is you fit one model, you fit a model that's nested within it. So you fit like one with 3 factors, you fit a model with 2 factors. You take a look at the log likelihoods, the difference in log likelihoods. -2 times the difference in log likelihoods follows a chi-square distribution where the degrees of freedom are the difference in the number of parameters. So ML gives you a lot more statistical evidence as to why the solution happens. So if you're going to do EFA, if you had to, ML is the way to go. But in ML, sure enough, there's no eigenvalue. There's no eigenvectors. There's no proportion of variance accounted for. We can calculate an R-squared per item. We can talk about how much variance the factor or the set of factors contributes on an item, but we don't get a total variance accounted for. So then you're in a situation where you're like, I'm effectively out of EFA for everybody who knows it anyway, because the Kaiser criterion or whatever that you want to use is no longer valid. Right? So ML, furthermore, one last thing about ML that's great is that if you have missing data, what did you do in your PCA? If you had like one person missing. List-wise deletion or pairwise deletion, probably, right? In ML, you don't have to do that. Whatever's missing, you can keep all the data you have. No deletion. And what that gives you a benefit of is the data themselves. There's certain, did you talk about missing data in Billy's class? I gave him all my notes. I don't know how much you used, though.
A little bit.
A little bit. So there's 3 features of missing data. There's 3 types of missing data we typically classify data as. Missing completely at random, missing at random, missing not at random. Have you heard of those? Missing completely at random is essentially like there was a glitch in the computer, random chance happened, gone.
Very hard to actually happen.
Exactly. It's a really hard standard. That's effectively what PCA is assuming if you have missing data. Missing at random is a lot stronger, saying the person didn't respond, but why they didn't respond you've captured with the other bits of the data. Right? So, hey, if that factor was the cause of it, and you know something about the other items, Jesse, you can go and sort of fill in what the idea is. So maximum likelihood also gives you better missing data protection. It comes at a cost. You have to pick a distribution, and most of those are multivariate normal, but you get all the good stuff with it. So if you're going to do this, use maximum likelihood. I'm going to go to why. Here we go. Why not to use the EFA framework? All factors predict all. Let's see. So one of the big problems is that all items are loaded onto all factors, and it's not possible mathematically without what we call identification constraints. So behind the scenes, even if you're using maximum likelihood, there are certain combinations of parameters that they're focusing on. I mentioned this kind of the product of the loadings that happens here. To give you, try to give you my mathematical, to try to prove to you that I know what I'm talking about. If you had a matrix of factor loadings, right? We'll call this lambda, right? This is our matrix lambda. And you had a matrix of unique variances. This is psi, right? So this is a items by factors matrix right here. And this is an items by items matrix. The constraints they impose in maximum likelihood EFA is the following. Right here, it's lambda transpose psi. I put little arrows on top of my matrices when I draw them on the board. Lambda has to be equal to a diagonal matrix delta. What is this? Delta is diagonal. This is a diagonal matrix, means it has numbers down the diagonal and zeros in the off diagonal. That's the set of constraints you're doing. Right? And so what happens in ML EFA is people talk about this, and they cite Lawley and Maxwell wrote a book in 1972 and said this is how you should do it. And this is what happens. If you go look up like in SAS, the proc factor, you do ML EFA, they say, yeah, we're using the method of Lawley and Maxwell in 1972. That's it right there. Those are constraints. It's doing this weird matrix product. Can anyone put into words what I just drew here? No. Neither can I. Right? And it's not a function of being familiar with matrices, because this has been sort of my career for the last over a decade, right? I do matrices a lot. It's because it's crazy, right? There's a set number of constraints. It specifies exactly the number of constraints that have to be there to make this work. And so the constraints are the big problem in this. So what do you need to do if you need to be somewhat exploratory, though? And that's where we're going to get into CFA. A lot of times what we do is use CFA to explore our data, mainly because we have control over the constraints, right? An alternative version of CFA. So in an EFA, all of these loadings are estimated subject to this constraint. In CFA, we get rid of this constraint and we say the following. If we had two factors here, if we say, yeah, the first item just didn't measure the second factor, we put a 0 there. That's an equivalent constraint. That becomes interpretable, right? Oh yeah, item 1, whatever that is, only measures this factor. Well, if you designed your study where you knew an item only measured one thing, that one thing became factor 1 when you do that. You don't need to rotate, you don't need to move things around. You can define the constraint, you can identify the constraint, you can actually argue for the constraint. It makes sense, and that's an equivalent model right there with a 0 to the same model with the EFA constraint here, right?
Does that mess up like the ability to measure the unit dimensionality of the subject as well as like the subscales?
No.
Or does it actually?
It makes a big, I mean, basically what's going to happen is you're going to really impose a lot of constraints in CFA. You're going to say, here's what I hypothesize the structure to be. And it's essentially a hypothesis test. Right? That's your null hypothesis. My data fit the model, I think. So you're going to collect data to try to reject that null hypothesis. So if you say, I'm measuring one thing, that's your hypothesis. If the data don't fit, you reject it. You're measuring more than one thing.
If you're measuring 4 things that you think form one thing,
you could test that as well.
So when you say, going back to what, there is no significant test for PCA or EFA for the loading.
For ML, there is a significance test in EFA, but for PCA-based versions of EFA, there's not.
Okay, so for the loading, we can't, when you say that for item 1, measuring construct 1, but not construct 2, assuming that we have 2 construct.
That's right, that's right.
So
there's no significance test for this, right? I fixed it at 0, right?
But still, if we do not fix it to 0, there is some noise there, like
maybe.
The noise that what I mean is that the loading, because the item 1 might load, for example, 80 in construct 1, but like 1 in construct 2. So
so there might be a number here other than 0. It may be, yeah. But you can actually tell it in other ways. So instead of figuring out whether it's significant or whether we're right about that, what we end up doing is we impose the constraints, and we have other methods to tell whether or not this model fit the data that we have.
Fitting indices, you mean?
Fit indices, that's right.
But still, the same problem, because the fitting indices like Tucker or root mean square, there is ranges like.
There are ranges. There are ranges.
So
Agreed.
there's some subjectivity there.
There is not what I prefer the maximum likelihood ratio test personally, and there is no subjectivity. That is a uniformly most powerful test. That is there's a proof by Rao in the 1940s that talks about 30s that talks about that will be the best under a set of assumptions that are some are strict, most aren't. That works. So yeah, but no, ultimately what we're changing is we're trying to provide a better statistical framework for arguing for what the structure is. Yes, there are drawbacks, right? We have to impose some constraints. If we're wrong, we should see that in model misfit. Alternatively, really what I talk about exploratory factor analysis, there's sort of these camps. There's confirmatory and there's exploratory, right? And a lot of times when people say, I'm going to go and confirm my analysis, and it's like, well, if my model doesn't fit, which is a common result, now what do I do? We start making modifications to try to see what model does fit. You're no longer fully confirmatory, you're sort of exploring, right? You're somewhere in between. But you're doing so in a way where you know where your model's working better. And I think the information, actually I know the information you get is much more powerful than you would get from an EFA.
Yeah, of course, yeah.
Right? Because the alternative, you talk about model fit indices. What's a model fit index in EFA? Exactly. What people use is proportion of variance accounted for if you're in a PCA. But that's not really model fit, that's just a description.
So when you're doing kind of this option where you're imposing constraints on it with CFA, how different is that from like EFA through CFA?
It's so the EFA through CFA has to impose constraints, but you're essentially imposing constraints and seeing how well they fit. And then if they don't fit, trying to figure out where the misfit's happening, and then reimposing constraints or modifying your survey. Sometimes things don't fit because you have bad items.
So it seems that like the null model will be the exploratory model for the CFA and impose model to CN.
So the other way around, actually. So the null model has to have fewer parameters than the alternative.
Maybe the other way around.
But with the EFA, because you have this set of constraints here, even when you don't do this, you effectively have the same number of parameters. Because you set your right. So if you have like an ANOVA where you've got like 3 groups, if you say groups 1 and 2 have the same mean, you're actually only estimating 2 means, right? So right? So or 4 groups, excuse me. So so I know what we're doing is sort of I'm sort of just not even talking about this. That sucks. Here, I'll just go through this. That sucks. It's terrible. Don't do that. Oh yeah, that's the other thing. Rotation. Do you have a favorite rotation?
The one that I know.
What's
Verimax.
Verimax.
Yeah.
Who has been taught something else?
Oblimin.
Oblimin. Anybody else? Who are your instructors' favorite rotations? Do they have one? Verimax.
Used to
The default.
What's that?
Verimax is the default.
It's the default. I like it. So Verimax and then Oblimin. Why do you rotate?
Try to fit them.
You don't like the solution. But moreover, what's the bigger picture?
Correlation.
There's an infinite number of values of the factor loadings that will fit the same.
What?
How does that make you feel? Because ultimately you can rotate them. So therefore they're not unique. That's not good. No. In a CFA, you remove the need for rotation. Right? Rotation is described as something you're using to help interpret the solution. Right? You're going to rotate to make it more interpretable. In CFA, you've built the interpretation by the constraints that you put in. Right? You're saying these items only measure this factor. Why? Because I wrote them to do that. These items only measure this factor. Why rotate them? You know exactly what's happening. So here's another thing that really gets me. So I haven't done a whole lot of research on this, but if you're using M+, again, their default is the geomin, I believe. And the default for geomin has this, criterion to rotate, but I believe they allow it to sort of be fudgy, like if it doesn't quite work, they just kind of lop off some of the numbers. Now, don't quote me on that. That's just in my reading of everything. I'm probably wrong, but doesn't that make you feel weird too? It's like, oh, I didn't like that, so I'm just going to rotate it and just, change the numbers a little bit, and then I'll just publish it. And you wonder why we have an issue with replication bias, or, issues, right? So, point is, we're trying to build a strong argument for our results, and a strong argument comes with, I know what these mean, rather than, I figured I tried Verimax, I tried Obelman, I used the default, right? So that to me is how it works. Anyway, blah, 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 blah. Rotation, that sucks. That sucks. Geomin, I got that one right. Sucks. Blah, 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 blah. We're getting toward the end of class here. All right, we're getting to factor scores. So the factor scores, because the loadings themselves that come out of an EFA are not unique, the factor scores are not unique. There's what we call factor score indeterminacy. So if you rotate the loadings, you have to rotate the scores, right? That's not good, right? If you don't get into grad, but if you don't get into grad school, just if you get your GRE score back, rotate it. Use your Obelman or your Geomin and just change some of the numbers, and you're fine, and you get in. It's okay. No, the reality of it is factor scores are used only when we have to, right? There's two issues. One is sort of the rotational indeterminacy, right, which talks about, if you rotate your loadings, the scores will change as well. The other is, so that goes away in CFA, right? Because when you don't rotate, you have that unique set of solutions. The scores still are not unique in that they're subject to the mean and variance of the factor, how you've identified the factor, but they're unique in order, right? So the person who's at the top will be the top regardless if the mean of the factor shifts or if the variance of the factor shifts. Actually, the same thing's true with EFAs. Well, actually, no, not true in EFA. So anyway, so factor indeterminacy is the EFA issue. In CFA, we still have not every factor is measured completely reliably. We still have the reliability issue. So you give a person a score that comes out of the model, that's your best guess. Well, that's the same as, believe it or not, summing a bunch of items. That's your best guess as well, because they're not necessarily reliable either. So either method still has this unreliability. And the way that we get around that is to use the structural equation model, bless you, where we simultaneously try to do the CFA and the prediction, or what we're doing afterwards, in the same analysis. Because ultimately the things that would be, that would have error, the error is partitioned. There's a certain variable for it where it's quantified and left apart from the part that you're talking about that you're trying to actually see. But there are other things. You can't always do an SEM, but there are other methods that you'll want to use. But effectively, it's like remembering that you have error in your scores moving forward. So, but the big picture, though, for today is that if you're using EFA, anytime that you want to rotate the matrix, that rotational indeterminacy of the loadings also applies to the scores as well, right? Which is not good. Okay, so big picture, wrapping up. I know I sort of flew over all the slides. They're great slides. You're welcome to read them. Pretty readable. If you have questions on them, please shoot me an email or send me. I have office hours at 9 this Friday. I wasn't actually there last Friday. I forgot to email you. I hope you did. Nobody looked for me, right? Didn't think so. There was nothing due or anything like that. But this Friday, I'll be in the CRMDA office suite, 455 Watson. I think I'm in room F. If you walk in around the corner, you can find me. F for factor, or F for something else. Anyway, you're welcome to come talk to me about any of this or the homework or anything like that too. Speaking of, one last thing about the homework, if you're in a spot where you don't have a data set and you need some help finding one, let me know as soon as you can, and I can either lend you some data or help you identify one that works. We'll make it work. About exploratory factor analysis. Exploring means trying alternatives, and the big label EFA, the methods that go with it, I don't like because of what I outlined there. They're unstable. When you get to move them to where you start to think that they might be good, like when you use a maximum likelihood approach, then you're using the same function that you'd use in CFA, and the only difference is which constraint you chose, and so why pick a constraint that you can't argue about because you can't describe? except for with matrices. So my argument is mathematical, but my argument is also, though, you know, the bigger picture, though, is there's sort of an in-between. And I think that's where you're getting to. And we're going to see that when we get to CFA as well. Things aren't going to fit the first time you try it. So you're sort of not confirming anymore. You're sort of exploring, but through use of confirmatory methods. So I think that's the best way forward. The best case scenario is you get things that match in each. But the more I've played with data, the more I've seen other people's data, the more I think that's just chance. I think it's just it just happens to be this time with this data set. There were 2 factors in the PCA, and there were 3 factors in the alpha factor analysis. And if you developed maximum likelihood, somehow you figured out there were 2 or something like that. And it was close enough to make it work. If you are using this, don't tell me about it. But yes, I know your advisors might need. Send your advisor to me. That's a good one. I'll do that on the board. John Poggio used to. We had a good debate about this, and I drew that on the board, and he stopped talking. No, I'm just kidding. He didn't stop talking. He still does. No, I told him I'd talk about him in here, so I hope that he can find what I say. I hope I'm not defaming him with this. It's just a difference in philosophy. I'm very adamant about mine. He's very adamant about his. Really, what you want to do if you are using this, apart from not telling me, is report every decision you've made. Right? And the big picture is, when it comes to reproducible science, there's sort of 2 different ways. There's replication, which is somebody tries the same study with a different sample. But then there's also reproduction, which is essentially somebody who can get the same results with your data. Right? And to do the latter, really, that's the documentation. That's where syntax-based approaches work. I know if you love SPSS because it has good defaults for this, you don't often save the syntax. That may not be replicatable or reproducible. Reproducible, I think that's the term they use. Anyway. So, any questions or thoughts? Have I scared you? No. Yes.
So, my maximum likelihood, it's just only comes to play in that PCA?
No, there are no methods in PCA that use maximum likelihood.
Yeah.
In EFA, that's right. So the hard part is that EFA and PCA have sort of gotten blended back in the 1930s. But realistically, EFA is this model. PCA is just sort of a matrix result. In the EFA world, in the model, to do the model the way the model was built, maximum likelihood is used.
Yeah. So for the other situations, ML is not used.
You don't use ML. There's no ML for it.
Okay. Even though we learn it in multivariate class.
Yes.
Okay.
Yeah. PCA is like the actual PCA version is this sort of matrix decomposition. That's all it is. It's sort of a way of taking a matrix and it's what we call a change of basis. It changes what sort of the orientation of all the vectors in the matrix. EFA, the model, isn't that. So. Yeah, everything that we're going to learn for the rest of this class also is going to be maximum likelihood based. And I'll say this, and actually, again, my thinking now, I'm much more of a Bayesian person these days, so there's a big fight between people who do maximum likelihood, who are called frequentists, and people who are called Bayesians. I don't know if it's a big fight now, but they're sort of the same thing. Anywhere that you can specify a distribution and sort of the model that says what the values of the distribution should be is maximum likelihood and Bayesian, and those are the methods that you're going to use in the rest of the class. So those are the methods you should be using because they're a lot more precise. They're a lot more, you can be a lot more specific about what it means, and you can test when things go wrong a lot better. Other thoughts or questions?
If I simulate the data based on CFA, can I use EFA rotation or something to reproduce?
Oh, you can try, and there are certain ways of doing it that'll work actually. Yeah, and most of the time it will work because the data are clean, they fit the assumptions of the analysis, and so for all the things that don't happen in real life.
Yesterday I used CFA first, then I used EFA, try to make the factoring kind of similar to the CFA. It can do, but you need to try different rotations.
Yes. The other thing I would say, if you're going to simulate data, try to violate this constraint here, where you have a non-zero on the off diagonal and see what happens. That's where EFA starts going haywire. So if things don't fit, the only way, typically this works for a lot of models that are out there. If things don't fit, the only way the model can recover is to add more complexity. Right, so you see this in factor analytic sense, in mixture models or clustering. You know, if you've seen mixture models where latent class analysis, if it doesn't fit a certain number of classes, the only way the model can get better is to add a whole number of another set of parameters, like another factor or anything else. And so that's one way to make it work poorly as well. All right, other questions or thoughts? One last thing for you. Did I just undo like 3 of your classes?
Yes.
Oh, yes. I should make this a 700 level class. Get in first. Anyway, see you all. See you Thursday.